Hello and welcome to another lesson of A-level physics. Today's learning intention is to know how the nucleus was discovered. By the end of today's lesson, you're going to know how the nucleus was discovered, you're going to know how the size of a nucleus was estimated by Ernest Rutherford, and you're going to verify the proportionalities involved in the Rutherford scattering experiment. Now, the first task I would like us to do today is to recap our knowledge of nuclear physics from GCSE. Now, there's 4 questions that I would like to have a go at. What was the plum pudding model of the atom? Why was it replaced with the nuclear model of the atom? Then I'd like to name the 3 types of nuclear radiation and, if possible, give me the structure. In other words, what actually are those 3 types of radiation? Pause the video now, write down your answers in full and then press play to check your work. So, the plum pudding model of the atom then basically had electrons scattered throughout a sphere of positive charge. Now, it might be that you've done a diagram to go along with that as well, which I've put up on the board for you now, showing a ball of positive charge or a sphere of positive charge with negative electrons scattered throughout it, like so. We were then asked, why was it replaced with the nuclear model of the atom? That is ultimately the learning intention for today, to be perfectly honest, but it was as a result of the Rutherford scattering experiment, which we're going to look at in more detail. There was evidence found from the Rutherford scattering experiment that couldn't be explained using the plum pudding model of the atom. The 3 types of nuclear radiation then are alpha radiation, beta radiation and gamma radiation. Well done if you got those 3. Now, an alpha particle is made up of 2 protons and 2 neutrons. A beta particle is a fast-moving electron from the nucleus, and gamma is a high-frequency electromagnetic wave that comes from the nucleus of an atom. Well done if you got all of those correct. Okay, now we're going to just delve into a bit of atomic history to begin with, and starting with J.J. Thompson. Now, J.J. Thompson had discovered the existence of electrons in 1897. We're going to do a lot more about that when we do the turning points in physics option. Now, he proposed, because he discovered electrons, which he knew were subatomic, they were smaller than the actual atom, he proposed that a neutral atom must have an equal number of electrons and positive charges. However, it wasn't known how these positive charges were distributed, which is why he came up with the plum pudding model of the atom. Obviously, he's a very, very well respected scientist because his breakthrough in discovering electrons was absolutely essential into understanding atomic structure. However, his plum pudding model was eventually found to be incorrect because of the experiments conducted by Ernest Rutherford in 1909. So, Ernest Rutherford then, actually a New Zealander, he arrived in Britain in 1895, and amazingly, and this is why I've labelled him here as having the character virtue of ambition, he was actually a professor by the age of 28, which is a staggering achievement. Now, Ernest Rutherford, as well as his students, Geiger and Marsden, they conducted what is now known as the Rutherford alpha scattering experiment in 1909, and from this alpha scattering experiment he was able to deduce the nuclear model of the atom. So let's actually look at what the alpha scattering experiment was then. Rutherford, along with his students Marsden and Geiger, essentially decided that they would fire alpha particles at a very, very thin piece of gold foil, and the experimental setup is shown there on the right-hand side of the board. So he fires alpha particles, which he knows are given out by radium, at thin gold foil. He used gold as opposed to any other element because he needed the target to be extremely thin. He wanted it to only be a few atoms thick. And gold was the most malleable metal that he had available to him at the time, so he was able to get gold to be thinner than he would have got any other material. Obviously, this experiment needs to be done in an evacuated chamber, otherwise known as a vacuum, and that is to make sure that the alpha particles didn't get stopped or absorbed by air molecules. You might remember from GCSE physics, of course, that alpha particles have a very short range in air, but obviously in a vacuum they'd be able to travel much further. The detector starts off straight in front of the gold foil so that any alpha particles that go straight through the gold foil without being detected are found by the detector. But that detector can be moved around the gold foil, maintaining a constant distance from the point of impact between the alpha particles and the target. Now, that detector basically has a microscope that is used to detect pinpoints of light when the alpha particles hit a fluorescent screen. Because when they do so, when alpha particles, because obviously the charge hit a fluorescent screen, that causes light to be emitted, and it would essentially look like little dots when viewed down the microscope. Now, the alpha source that is being used for this experiment needs to have a long half-life. The reason for that is they will set up the experiment as shown here, and probably start with the detector straight behind the gold foil. Now, obviously, they then move the detector to see how many alpha particles are being detected in a certain amount of time at different positions. But if the half-life wasn't long, then what we would find is that later readings will be much lower than the initial readings because of the decay of the nuclei and therefore the loss of activity of the source. That would obviously influence the results drastically, so we need to make sure that the alpha source has a long half-life. As well, the alpha particles all need to have the same kinetic energy. The reason that the alpha particles all need to have the same kinetic energy is because obviously a slower moving alpha particle will potentially get deflected considerably more than a faster moving alpha particle, because any force causing deflection would act on it for a longer period of time. Now, what Rutherford obviously found with Geiger and Martin was that the vast majority of alpha particles did go straight through the gold foil undetected, or with very, very slight deviations as shown on the board. However, they did find that 1 in 10,000 alpha particles were deflected by more than 90 degrees. That is a very, very significant finding for this experiment, because what that goes on to show us is, of course, that the vast majority of the atom is made up of empty space, but there is a very, very dense nucleus where the vast majority of the mass is stored within the atom, and that must have a positive charge in order to repel the alpha particles, which Rutherford, of course, knew were positive. He used those findings to then, of course, come up with the nuclear model of the atom, suggesting that most of it was empty space, but the nucleus was positive and contained most of the mass of the atom. Now, what I've got on the board here is a diagram that shows the path that alpha particles would potentially take through that gold foil. Now, you can see there that the further away the alpha particles are from the gold nucleus, the lower or less deflection actually happens. So for the one that is furthest away, that just has a straight path because it's a long way from the gold nucleus. The one up from that has a slight deflection, and then obviously when you get up to the one that's very close to it, you can see that gets deflected by more than 90 degrees, and then the alpha particle that's heading straight for the gold nucleus actually does a 180 reverse. It is important that you study that diagram, because you could well be asked to complete the paths shown by different alpha particles when they're passing through an atom, and you would need to show that the closer they are to the nucleus, the bigger the deviation in their path would be. So what then goes on from here is Rutherford has come up with Rutherford has come up, of course, with the nuclear model of the atom, but he's also able to estimate the size of the nucleus, and he does that using a distance of closest approach method. As an alpha particle travels towards a gold nucleus, it gets very close to it, but then obviously will get stopped before reversing and doing a 180-degree U-turn, if you like. Now, at the point where the alpha particle stops momentarily, the alpha particle, of course, will have no kinetic energy. The conservation of energy means that the electric potential energy at that point must equal the initial kinetic energy of the alpha particle. In essence, the alpha particle did have kinetic energy. As it's approached the gold nucleus, that kinetic energy has got lower and lower and lower, because the electric potential energy that it's getting due to the gold nucleus is increasing. So we can use the conservation of energy to work out how close that alpha particle gets to the gold nucleus, i.e. the closest approach of it. So, example that we're going to do together then, if we've got an alpha particle, which of course has a charge of plus 2e, because it's 2 protons, 2 neutrons, if that has a kinetic energy of 1.2 times 10 to the minus 12 joules, and it's fired at a gold nucleus, which has a charge of plus 79e, then work out the distance of closest approach. I'll show you how to do this calculation together. I want you to obviously follow it through with me. So, on the formula sheet, there is an equation for electric potential. Electric potential V is Q over 4 pi E naught R, where Q is the charge of that nucleus, E naught is the permittivity of free space, and R is the distance from that nucleus. However, electric potential is not the same thing as electric potential energy, because electric potential is electric potential energy per unit charge, and so the actual equation for electric potential energy, which isn't on the formula sheet and you would need to know, is Q, charge of the alpha particle, multiplied by Q, charge of the nucleus, divided by 4 pi E naught R. So you need to know the electric potential energy of that alpha particle a distance away from the gold nucleus will be given by this equation. Now, we've said earlier on the previous slide, of course, that due to the conservation of energy, the kinetic energy lost by the alpha particle is equal to the gain in electric potential energy gained by the alpha particle as it reaches the nucleus. And so from there, what we can essentially find using a little bit of maths is that R, the distance of closest approach, will come out as being 3 times 10 to the minus 14 metres. If you weren't able to get there yourself, you would just substitute values into this equation. So EP will be equal to the kinetic energy, which is 1.2 times 10 to the minus 12. 4 pi is a constant. E naught is on the formula sheet as 8.85 times 10 to the minus 12. And then Q and Q, the charge of the alpha particle will be 2 times 1.6 times 10 to the minus 19. The second Q will be 79 times 1.6 times 10 to the minus 19, and obviously you would then rearrange this equation to get a value of R. Okay, so that calculation gives us the upper limit for the radius of a gold nucleus, but more accurate experiments using the diffraction of high energy electrons have since shown the radius of the nucleus to be around 10 to the minus 15 metres. That is 10 to the 5 times smaller than that of an atom, which is obviously minute by comparison. We're going to do more about the diffraction of high energy electrons in our next lesson. Okay, I would now like us to have a go at some summary questions. We've got grade B and C questions first of all, and then the grade A summary questions. Pause the video and have a go at these questions. So, question 1 said state the approximate radii of an atom. So an atom, you should know, is about 10 times 10 to the minus 10 metres. The radius of a nucleus we've found is 10 times 10 to the minus 15 metres. Then it says the diagram shows the path of an alpha particle close to a nucleus of lead. Draw arrows to represent the force on the alpha particle when at points A, B and C. So the way we would do that then, obviously the force is a repulsive force, so it needs to go away from the lead nucleus. And if we look at A, you would draw it in that direction. It is important that if you were to extrapolate that force line, it needs to also go through the lead nucleus. If you just drawn an arrow in any old direction, but sort of the right one, the examiner would check that it extrapolates to go through the the lead nucleus. Now the arrow for B not only also needs to go through the lead nucleus when extrapolated, but it needs to be a bigger line as well because the magnitude of the force is bigger, and remember we show the magnitude of a force by the length of the arrow. So B, because that is closer than A, needs to have a longer arrow. And then C finally will be drawn in that direction, following on with the exact same rules that we've already established, that that line needs to extend back to go through the nucleus. Question 3. In the Rutherford scattering experiment, why was it essential that the gold was very thin? So the gold has got to be thin so that it is only a few layers of atoms thick. Otherwise, the alpha particles may be scattered more than once or by more than one atom. Part B. The beam of alpha particles very narrow. Why does it need to be very narrow? Well, the reason that the beam needs to be narrow is so that we can tell if an alpha particle has passed straight through the gold or if it was slightly deflected. If the beam was really wide, a slight deflection might appear as if it has gone straight through anyway. So obviously having a narrow collimated beam means that we can be confident when particle has been slightly deflected. Okay, part C says, why was it essential that the alpha particles all have the same speed? So they all need to have the same speed and the same kinetic energy, Otherwise, slower alpha particles will be deflected more than faster moving alpha particles along the same initial path. Part D. Why was it important that the apparatus was in an evacuated chamber or a vacuum? The alpha particles would obviously be stopped or absorbed by air molecules, and we don't want that to happen because that would influence the results of the experiment. Question number 4. Rutherford estimated the diameter of a nucleus using a distance of closest approach method. What experiment has since improved the accuracy of estimates of nuclear radii? Well, that is, of course, as mentioned before, the diffraction of high energy electrons, which we will do more about next lesson. Okay, grade A questions. What we've got here on the board is a set of results, the actual results obtained by Rutherford, Marsden and Geiger during the original alpha scattering experiments in 1909. We've got there the different angles that the detector was placed at and the number of alpha particles being detected at those points. You can see that they range quite drastically, 132,000 at 15 degrees down to just 33 at 150 degrees. We want to use these results to show that the number of alpha particles scattered through a particular angle is inversely proportional to sine to the 4 of theta over 2. Now, let's begin by, of course, considering what inverse proportionality actually is. To be inversely proportional, that would mean that the number of particles multiplied by sine to the power of 4 would have to, of theta over 2, of course, will come out as being approximately a constant value. So, I would add an extra row onto that table to work out what sine to the 4 of theta over 2 is for each of those angles, and you can see that I've done that there on the left-hand side of the board. We then need to pick different pairs of values to check that they multiply to give a constant value. So it doesn't matter which one you pick, but I'm just going to pick 477 and 0.063, which we would find would multiply together to give a value of 30. So that's the constant that I've established. I could then pick a different value, say for theta equals 120, and that would do 52 times 0.56, which comes out as 29. Now, doing two values is never enough. It's very tempting to think, oh, 30 and 29 are similar, so I'm going to say that they're inversely proportional, but the exam board would expect you to do a third value. Doing a third value, I've decided to do theta as 150, so that means I'm doing 33 multiplied by sine to the power of 4 of 150 over 2. That again comes out as 29. So now that I have three pairs of values that are giving me the same constants, I can then conclude quite confidently, of course, that n is indeed inversely proportional to sine to the power of 4 of theta over 2. Question number 2. An alpha particle with an initial kinetic energy of 4.9 mega-electron volts is directed towards the centre of a gold nucleus of radius r, which contains 79 protons. The alpha particle is brought to rest at s, a distance r from the centre of the nucleus, and we want to calculate the value of r. What we're essentially being asked to do here is actually work out the distance of closest approach, which is what we did in an example earlier on. First thing I'm going to do though is put that energy value into joules. So 4.9 mega-electron volts could be written as 4.9 times 10 to the 6 electron volts, and then I would multiply that by 1.6 times 10 to the minus 19, which is the charge of an electron, to get the energy in joules to be 7.84 times 10 to the minus 13 joules. Now that I know that, I then now need to apply a bit of physics. Knowing, of course, that the kinetic energy of the alpha particle is transferred to the electric potential energy, then I can, of course, set out those things equal to each other. So electric potential energy is QQ over 4 pi E naught R, and that value of EP is going to be 7.84 times 10 to the minus 13 joules. I rearrange this equation for R, so I'll multiply up by R and divide by electric potential energy, and then substitute the values in. So 2 times 1.6 times 10 to the minus 19 is the charge of the alpha particle. 79 times 1.6 times 10 to the minus 19 is the charge of the gold nucleus, and I divide that by 7.84 times 10 to the minus 13, which is the which is the kinetic energy or the electric potential energy, multiplied by 4 pi 8.85 times 10 to the minus 12. That, of course, comes out with a final answer of 4.64 times 10 to the minus 14 meters, which is the final answer. Okay, and part B says explain without further calculation how the value of r, the distance of closest approach, would change if the target nucleus was changed to one of fewer protons in it. Assume that the alpha particle has the same initial kinetic energy and ignore any recoil effects. Well, if that nucleus has now got fewer protons in it, that means that the charge on it is going to be reduced, because it's the protons that, of course, give the nucleus a charge. If the charge is reduced, then that means the electrostatic repulsion on the alpha particle is going to be less. So therefore, to reduce the kinetic energy of the alpha particle to zero with a smaller force acting on it, that force is going to need to act for a much longer time, meaning that the alpha particle is going to get much closer. So therefore, what we can say about the value of r is that it is going to be smaller. The electrostatic repulsion between the alpha particle and the nucleus is smaller, and so it needs to travel further to lose the same initial kinetic energy.